Okay, hello everyone. Welcome to this month's COFFIES Seminar. Today we will have Dr. Loren Matilsky to give a talk about their recent work. It's my honor to introduce the speaker today. Dr. Loren Matilsky is an NSF Astronomy and Astrophysics postdoctoral fellow at the University of California, Santa Cruz. He is also a COFFIES member of the Tachocline and near-surface shear layer themes. He works primarily with Professor Nicholas Brummel on stellar dynamo theory. He graduated in physics and mathematics from Cornell University in 2015 and received his PhD in astrophysical and planetary science from University of Colorado Boulder in 2022, advised by Professor Yuri Tomori and Bradley Heidemann. Dr. Matilsky's research focuses on the behavior of stellar dynamos in both partially convective G-type solar-like stars and fully convective M-dwarfs, particularly as these stars spin down over time. Today, he will talk about his recent work about the dynamo confinement scenario for a radiatively spreading tachocline. And let's welcome him again. And Lauren, you have the Zoom now.
Great. Thank you for that very nice introduction. And I'm excited today to discuss some recent work that I've done with Nick and collaborators on the solar tachocline. And so the first part of this talk is really an announcement of what we did. There's a short AppJ letter that I'm going to describe that's now in press. And then I'll end with some avenues for future directions that I hope we can explore through COFFIES. So I always put all my colleagues and their faces on the relevant work, and so you'll see everyone's names and faces pop up when I discuss the relevant papers. So I have a little more intro than probably is necessary for this crowd, but if we take a step back, then we're interested in how sunspots form and what causes the flux emergence and the solar cycle. So I won't go through all of this because I think a lot of people are familiar. But the goal is to figure out, how the cycles form. And let me just jump to, sorry, I borrowed some slides from another talk. The real question of solar physics is the dynamo problem. Why the heck is the dynamo so ordered? So sunspots emerge first at mid-latitudes and then progressively closer to the equator, making the famous butterfly wings. We have Hale's polarity rules, so the leading edges, the leading sunspots emerge with one polarity in the north and south. And this makes a 22-year cycle overall. And so there's ongoing work in COFFIES to understand why this cycle is so intricate. And the reason I mention it is that the tachocline is often thought to play a key role in this problem. So the solar tachocline, as everyone probably knows by now, is the place where the strong latitudinal differential rotation in the convection zone transitions at the convection zone's base to rigid rotation in the radiative interior. And so the region between is a tachocline of shear. Tachocline means it's all converging to the same speed. And it's, as far as we know, located roughly at the base of the convection zone, although the exact location, maybe we don't know. And then the transition width is exceedingly thin. We don't exactly know how thin it is, but it's certainly less than a few percent of the solar radius, which is the width of the seismic inversion kernels used to make the measurement. Just for newer people, if there's any in the crowd, this is a plot of the rotation rate of the inside of the sun as a function of radius and latitude. So the equator is on the x-axis, rotation axis on the z-axis, and then a red color means fast rotation, blue means slow, and the tachocline is where all these isocontours of rotation converge to the same rotation rate, this yellow region in the radiative interior. So because this region is associated with extremely strong shear, it's thought to play a key role in the solar cycle by shearing colloidal field into toroidal field that spawns these buoyant flux ropes that emerge at the surface to form sunspots. And today I'm going to discuss a slightly different scenario in which I think what we're finding is that maybe the dynamo itself plays a key role in the dynamics of the tachocline. So not only could the tachocline play a key role in causing the dynamo, but the reverse maybe could also be true. So what are the dynamics of the tachocline? And there's something of a mystery because when the tachocline was discovered, it was realized that it should spread over time if left to its own devices. Um, so this is a sketch of the seminal paper by Ed Spiegel and John Paul Zahn in 1992, shortly after the tachocline was discovered. And what they found is that through a process that's well known in the atmospheric literature, it's called downward control or circulation burrowing. Basically, what happens is the radiative interior is extremely strongly stably stratified, which means that convective plumes, as they overshoot, are strongly decelerated, and there should be very little radial motion in the radiative interior. And so you might think that a shear layer at the top of the radiative zone could be understandable because the stable stratification would prevent the shear from spreading. But through this process of circulation burrowing, or it's called radiative spreading in the sun, actually, the tachocline should spread significantly by the solar age. And so the way this happens is that the fluid is assumed to be Boussinesque, so you effectively get an incompressibility condition. It's also assumed to be in thermal wind balance. Thermal wind balance here means that the axial, the z derivative of the rotation rate is in balance with the latitudinal temperature gradient. And then finally, the circulation is also achieving an advective diffusive balance of heat. So there's this strong stable stratification. That's this n squared, the buoyancy frequency, and that's in balance with a radiative thermal diffusion. And that's why it's called radiative spreading, is because this kappa, the thermal diffusivity, is predominantly radiated. And so if you count the number of derivatives, well, okay, first you can consider what the circulation is how it's gonna transport angular momentum, because the system is gonna evolve as the circulation spreads inward. It carries angular momentum with it, and so you can count the number of derivatives in this equation, and you get 4 of them, and so you get, in summary, that the rotation rate of the radiative interior should grow like the 4th power of the gradient in the tachocline. So this is the fourth radial derivative. And the reason that's important is this occurs on the Eddington sweep time, which is extremely long. The Eddington sweep time characterizes the deep circulation in stellar radiative interiors, and for the sun, it's a few hundred billion years. Nonetheless, because this is such a fast process with the 4th power of the derivative, the tachocline should have spread significantly inward. So by the current age of the sun, if this radiative spreading were left to its own devices, then the tachocline would have spread to about 30% the solar radius. So something must be stopping this tachocline from spreading. That's the main point. So there needs to be some process in the radiative interior that produces a torque that prevents radiative spreading from doing its thing. So I'm moving quickly because I think a lot of people are familiar, but it's always good to remind ourselves. So there's a few different origin stories for this unknown torque, which are called confinement scenarios. So the first one was laid out in Spiegel and Zahn, 1992, in that same paper, and they argued that because of the strong stable stratification, there would be predominantly horizontal turbulence with very fast horizontal velocities compared to slower vertical velocities. And they argue that this should homogenize angular momentum on spheres and could lead to a confined tachocline in this case. So this scenario has sort of um, been explored in other avenues using fundamental results on stratified turbulence. So if you want to know more about this, Pascal Garot, Douglas and me wrote a nice paper that summarizes some of the recent work that was published at the beginning of this year. But what I'll be discussing today is a magnetic confinement scenario. And so this was argued by Goff and McIntyre in 1998 because they said these shear instabilities that were supposed to produce that anisotropic turbulence probably wouldn't drive the system toward uniform rotation. Instead, they would drive it away from uniform rotation. And they argued that there had to be some magnetic mechanism. And for them, it was a primordial dipolar magnetic field in the radiative interior that would stop this burrowing circulation. And so as the circulation carried the differential rotation inward, that differential rotation would try to shear these colloidal magnetic field lines. They'd feel a resistance because of magnetic tension, and that would confine the tachocline. And these two sort of hydro shear instability and then MHD primordial field scenarios are kind of the two competing um, scenarios we think for tachocline confinement. And there's another flavor to the magnetic scenario, which is the one on the right. Maybe you could have the solar cycle itself from the 22-year cycle impinge into the radiative zone to some skin depth, and then that could provide a reversing magnetic field um, that could take the place of the primordial magnetic field or maybe work in concert with the primordial magnetic field and confine the tachocline that way. And that third, the flavor of this scenario where the dynamo actually confines the tachocline as well, I'll be discussing today. Okay. And the main point of the, so a few years ago, we published some work where a tachocline was confined self-consistently by a dynamo in global simulations. The problem with that work was that it was not confining things against radiative spreading. So it was really confining things against viscous spreading because the viscosity was too high. And so the goal of this work was to get into the correct parameter regime where we think radiative spreading is occurring. And to do that, we need to understand what sets whether viscosity or radiative spreading is what spreads the tachocline. And that's governed by what's called the sigma parameter. There's two spreading mechanisms. There's viscosity, which tends to dominate in simulations, even though it's thought to be negligible in the sun, and then the radiative spreading that we just discussed. And so what you can do is you can take the ratio of these two timescales. So there's the Eddington-Sweet timescale, which is, I didn't write the formula for it, but it's basically a thermal diffusion time lengthened by the stable stratification. So there's an N over 2 omega, where omega is the rotation rate that comes into this. So if you take the ratio of the Eddington-Sweet time to the viscous diffusion time, then that tells you which of these processes is quicker, viscous spread or radiative spread. And that's a combination of two non-dimensional numbers. There's this buoyancy number, which is that n squared, the buoyancy frequency divided by 2 times the rotation rate squared, and there's a Prandtl number, the ratio of the two diffusivities. And we expect that if the sigma is low enough, then the burrowing circulation is thought to spread the tachocline inward. For high enough sigma viscosity, or for too high sigma, viscosity will spread the tachocline. And so the situation before was that the sun is in the region up top where it has incredibly small Prandtl number, very high stable stratification, and this results in a sigma of about 0.3, and so it's firmly in this radiative spreading regime. And then typical simulations are run with a Prandtl number of 1, a buoyancy number. This is a historical choice, but typically we want the system to be strongly stably stratified because in that sense it's solar-like. But then if you do that, then sigma becomes very high. And so these are all viscously spreading tachoclines. So what we did in this new work is we basically made the Prandtl number small. I think these are a little bit out of date. So it's 0.25, buoyancy number of about 6. So it's at least pretty stably stratified. And then sigma of about 3, which is bigger than 1, but as we see later, it's still small enough that radiative spreading occurs. So that's the name of the game, is to kind of try to edge the system to be slightly more solar-like, at least in the sense that radiative spreading occurs, even if some of the other numbers are very far off from where we want to be. Okay, and the reason is we can't just do the solar case is that if we tried to do Prandtl number of 10 to the minus 6, we would require way too high resolution because the turbulence level would be so high. Okay, so I just said in words discussing these non-dimensional numbers why this problem is so difficult. And I think it's helpful to understand why we can't just do the full problem right away. And this slide is basically showing the parameter regime that the sun is in terms of timescales. And the problem is that we have all these different timescales. There's a buoyancy gravity wave time, there's Rossby wave timescales, there's the turnover free fall time, and these are ranging from 20 minutes to a few days to several trillion years for the diffusion times. And so all of these processes seem to be relevant for things like radiative spreading, um, and and uh, and and the dynamo cycle, and we just can't, there's no way we can resolve the fast timescales compared to the slow timescales. And so this is just another way of saying that what we're doing in the simulations is that we're smudging all these different timescales together, um, and we're mixing them around. So some of the physics is going to be messed up, but the goal here is to at least get the Eddington sweet time and viscous diffusion timescale ordering correct, because in prior simulations, um, we had uh, we had the viscous diffusion time reversed from Eddington Sweet. And the point of this slide is to show that when I say we're trying to do the solar regime, we're focusing on one aspect of the solar regime. There's a lot of other aspects to this that are not solar-like, and so it's important to bear that in mind. Okay, and this is another way of saying this in terms of non-dimensional numbers. We won't go into it too much, but the main point is that some of these numbers are like, 10 to the minus 6, 10 to the 22, 10 to the minus 14, and we can't do that. And this slide can also be referred to later if you need to know the definition of any of these non-dimensional numbers. Okay, so how do we go about solving these equations? We use the Rayleigh code, which is an open source software developed by computational infrastructure for geodynamics. And we solve the anelastic magnetohydrodynamic equations. So these equations are listed here. They're the standard fluid equations, but in continuity, we have a divergence-free mass flux, and we also linearize the thermodynamics so that in the buoyancy, the we sorry, we're assuming small thermal perturbations, um, and we linearize them about a hydrostatic reference state. And so the buoyancy terms and pressure terms are assumed to be small relative to the background stratification. And then we evolve these equations forward in time, and we implement the stable stratification in the radiative zone through a background buoyancy frequency, effectively is n squared bigger than 0. And we drive convection in the convection zone with an internal heating that represents radiative heating from below. Okay. Um, the geometry that we're trying to assess, well, the question that we're trying to answer is, can the solar dynamo confine the Tachocline? That's really the essential question. Um, and our simulation geometry has the radiative zone below a convective zone. There's misaligned gravity in the radial direction and rotation in the z direction. Um, and it's a magnetized spherical shell. And we initiate the simulation with a random small amplitude magnetic seed magnetic field, and we let a dynamo develop and confine a Tachocline. And we're doing this, which might seem a little bit crazy to do, but we're doing this because a few years ago we showed that this was at least possible in the viscous case. So we think maybe it should be possible in the radiative spreading case. This is what one of these simulations looks like. Now we're getting into the published AppJ letter. So what I've done here is I'm showing in this 3D spherical cutout different surfaces of the simulation, and the outer part for in the convective zone, I'm showing the axial vorticity. So the vorticity traces the rotating convective structures. In this case, they're Busse columns or Taylor columns. Those are what drive the differential rotation. They drive the thermal wind balance. So you can see them, they're kind of like the banana cells on the outer surface, and then these cylindrically aligned columns if you actually go into the interior. And these are what causes the Reynolds stress that drives the differential rotation. They also help drive the dynamo because there's differential rotation, and they form the helical convection that makes something like an alpha omega type dynamo. Then in the interior, in the radiative zone, I'm showing the poloidal magnetic field. And so what you can see is that there's this large scale poloidal magnetic field that is due to a convectively excited dynamo that has diffused all the way into the radiative zone. It's a non-axisymmetric poloidal field, and this is what we've found is what confines the Tachocline. Okay, so this is from the radiative spreading case. And how do we know that it's actually a radiative spreading case? Well, we can go back to the confinement work that we did against viscous spreading. And so this was another paper in 2022. This is the first publication showing that this was possible. And what we had then was two cases. One was at sigma, they were at sigma of 80. So this was firmly in the viscous spreading regime. And what we can do is we can look at, sorry, I'm jumping around a bit. We can look at which processes spread the angular momentum inward, and then figure out figure out which processes are spreading angular momentum inward in the radiatively spreading case. Okay, and I'm going to jump back, Nick. Maybe Nick's worried because I skipped over a bunch of important stuff, but I'm going to jump back for that. I should have reordered these slides when I had the chance. Anyway, for the viscous spreading case for sigma of 80, the reason we knew it was viscously spreading was because you can actually look at the torque balance. And so what's happening is you start with a rigid rotation everywhere, and then there's differential rotation that develops. This is showing the differential rotation in this viscously spreading hydrodynamic case. And so what happens is there's some torque that spreads the differential rotation inward. The net effect, if you integrate over the whole region ends up spinning down. And what you can do is you can plot the actual angular momentum of the system in the radiative zone as a function of time, and then plot the integral of all of these different torques that could be causing the angular momentum to change. And so what you see in this hydrodynamic case, which is not confined, is that the the angular momentum goes down, it becomes negative, and it's driven primarily by the viscosity. And so that's why we call this a viscously spreading case. So the torques are listed up here for convenience, but the point is that the other torques, the Reynolds stress torque and the circulation torque, aren't causing this shear to spread inward. It's only the viscous torque that causes the spreading to occur. Then when we looked at the magnetically confined case, now there's two new torques. There's one from the non-axisymmetric field, one from the axisymmetric field. We know the tachocline got confined, and what you can see in the torque balance is that the angular momentum, the thing starts to spin down due to the viscous torque, but then this Maxwell stress torque comes into balance with the viscosity, and that's what confines the tachocline. And so the goal is to redo this analysis in the radiative spreading case, because these slides were still on the simulation from a few years ago, and to redo this analysis to make sure that it's the circulation, this burrowing circulation, that's what's spreading the angular momentum inward. Okay, so that's just an intro to what we'll be doing. The other thing that we want to check is that this viscously spreading case had a number of other intricacies on how this scenario worked, and we want to make sure that those remain robust. So in particular, what happened in the viscously dominated case is we had the primary dynamo mode being non-axisymmetric, so azimuthal wave number of m equals 1 or 2. This shows spherical slices of the horizontal field in the top row as near the base of the convection zone. B phi and B theta are clearly correlated, so they make these Maxwell stresses that transport angular momentum poleward and confine the tachocline by eliminating the fast equator. And then the imprint of this, as the magnetic field diffuses into the radiative interior, you can still see the imprint of this horizontal field and the Maxwell stresses. And you can think of this in terms of magnetic tension, similar to the Goff and McIntyre scenario. These field lines don't want to be bent, and they're non-axisymmetric in this case, and so the only alternative is basically rigid rotation. And so we want to see if this non-axisymmetric mode sticks around. We think it does because we already plotted it in that first plot for the radiative spreading case. And then the other thing we want to see is how the cycle spreads inward. Because in the viscously dominated case, what we found was that if you make this time radius diagram of the non-axisymmetric field, so that's similar to a butterfly diagram, but now radius is on the y-axis. The field first forms at the interface at the base of the convection zone and then goes inward. And it seems to do so at a rate that's consistent with a skin effect because it's a reversing magnetic field. The skin effect is basically where you have some oscillating phenomenon at the boundary of a fluid, and then it diffuses into the fluid with an exponentially damped envelope because you're moving things back and forth. So as one pulse of one sign goes in, there's another pulse of the opposite sign going in, and they kind of cancel out. And there's an exponential damping called the skin depth. That's basically it ends up being the square root of the diffusivity divided by the frequency. So high frequency things don't penetrate as deep, and low frequency things penetrate deeper. And this skin effect was actually shown to be describe this system exceedingly well. So what we could do, and what we did in some follow-up work in 2024, was we took this oscillating magnetic field at the interface and we took its frequency spectrum and we computed a bunch of different skin depths. So some range from very shallow to very deep, and we weight them by the actual amplitude of the field at the surface. We add all these damping profiles together, and then we compare with what the field actually is in the radiative interior. And so it matches here the skin profiles are shown in these solid curves, whereas the actual achieved magnetic field is shown as the dots, and they just match up quite well for a number of different cases. Um, and so so it seemed that this skin effect was holding quite well in the viscously spreading case, and we want to verify that it's holding well in the radiative spreading case as well. Okay. So that was all still describing what we're about to do. Um, we talked about how we can figure out which spreading process is occurring in the simulations. And now we want to look at the radiative spreading case with sigma of 3 to show that it's actually radiatively spreading. Okay, so this is discussing the work with now Lydia Corey and Nick Brummel in this recently published letter. So it should be out soon. It's on the archive. It has the title Dynamo Confinement of a Radiatively Spreading Solar Tachocline, revealed by self-consistent global simulations. So you can find that. I think I did not put the archive link, unfortunately, but it is on the archive. And so what we found is that we can look at two cases similar to the publication from 2022. We can look at a MHD case, well, purely hydro case on the left, and a MHD case on the right. And in this case, what we were doing is we were initializing the system with a initially confined tachocline similar to the situation Spiegel and Zahn were considering. So we begin the simulation with a tachocline, but then we implement the parameters with a parental number less than 1, a sigma of about 3, and see if, first of all, if radiative spreading spreads the differential rotation inward in the hydro case, and then if the magnetic field can stop it. And so we find both these things. So we find that the radiative spreading does spread the differential rotation all the way inward. And then in the magnetic case, the spreading is stopped by the Maxwell stress. So this is good. So order 0, it worked. Dynamo confines the tachocline. You might be like, well, you still haven't shown it's radiatively spreading. So the way we can figure out that it really is radiative spreading is doing the same torque analysis. So we can look at the torque equation in the hydro case. So the same thing is happening. The radiative zone is spinning down. So we integrate over the full region, and we look at the angular momentum and the integrated torques. And so the integrated torque that seems to be spinning down the radiative zone is, in fact, this meridional circulation torque, which is the key signature of radiative spreading. Then the viscosity is still, unfortunately, there. It's a lot higher than we'd like. But this is kind of the best we can do in these simulations, where we at least get the radiative spreading to be working, and then viscosity is pesky, but it's basically there to balance the circulation once it spreads inward. And this was also shown by Lydia Corey and Featherstone 2024, that this type of balance is a signature of radiative spreading. So we're fairly confident that the radiative spreading is now occurring. And then we can look at the magnetic case. And in the magnetic case, now there's 2 more torques again. Now viscosity is annoying. It's still there, but it's weaker amplitude than the meridional circulation. So the circulation is still what's trying to spin the system down, and it's still the Maxwell stress that ends up stopping it. So this really is a radiatively spreading analog to the publication of 2022. And we're really excited about this because this is more solar-like. Radiative spreading is the process that we believe uh, should be spreading the tachocline in the sun. And so this new work, we hope, suggests that the Dynamo confinement scenario that we previously identified might remain robust in a more solar-like context. So that's the takeaway from this letter. It's basically an announcement that um, this type of process works. As far as we know, it's the first global rendering of a self-consistently confined tachocline against radiative spreading. Um, but the main takeaway is that it can work at least one time, and we want to figure out if it works in general, and in particular, can it work in the actual sun? Okay, so to that end, we have also considered a number of other less stratified and more stratified cases. And so what we ended up doing is Lydia and I have a number of simulations in different parameter regimes with slightly different geometries and background states. Uh, and we ended up realizing we're in fairly similar parameter regimes. And so we combined forces and we collected a whole bunch of radiatively spreading tachocline simulations. Um, and we ordered them in terms of this buoyancy number. So the buoyancy number was the n over 2 omega. And so what I'm showing on the lower plot is the two cases that we just published in the letters. So this was the 2022 viscously spreading tachocline. That's case M0. This was the just published radiatively spreading tachocline. And these are ordered so that these are all low sigma on the right. So these things separated by the um, purple line are all in the radiatively spreading regime, but they have different stiffnesses. So there are different stable stratifications. There's less stably stratified on the right, more stably stratified on the left. And it seems like what happens is even within this radiative spreading regime, as you um, change parameters from less stiff to more stiff, the tachocline gets progressively more confined. Um, so we're still working out how this plays out and the relationship to the solar case. The reason that this might be nice is that if we recall, the solar sigma is low because the Prandtl number is exceedingly low, but this stable stratification is very high. So it seems like maybe as we nudge these simulations to slightly more solar-like parameters in terms of increased stratification, that the tachocline, the dynamo confinement scenario of the tachocline behaves better and better. So this is a subject of the upcoming sequel paper to our just published letter, and we hope it will be out before too long, hopefully by the end of the year. And you can keep your eyes peeled for that, maybe in the COFFIES newsletter. Um, okay, so let me wind up before I confuse anything else. Sorry, I was a bit scattered today. All right, so where are we with radiatively spreading tachoclines? So I call this slide the good, the bad, and the ugly. So let's start with the good. So first of all, radiative spreading clearly occurs for low sigma. So at least we can get into the right parameter regime, the more solar-like parameter regime. Um, Great thing is that Maxwell stresses can stop the radiative spreading. So this dynamo, we've been calling it a dynamo confinement scenario. Um, the the dynamo can self-excite in the convective zone. It can diffuse via skin effect into the radiative zone and can produce Maxwell stresses that can stop the radiative spread. So this is very nice. This means that this scenario could be robust in the real sun. So the one thing that I glossed over and is kind of hidden in my color bars um, is that the Maxwell stresses also destroy much of the differential rotation in the convective zone as well. And so if you look at the color bars here, you know, these are, I'm plotting the rotation rate normalized by the frame rate. And so the deviation is about 1. And so these are on the order of a few percent differential rotation in the convective zone. So that's not so good. In the real sun, the differential rotation is 20 to 30%. So these simulations are producing a tachocline in the sense that the differential rotation in the radiative zone is eliminated much more effectively than the differential rotation in the convective zone, but unfortunately the magnetic field is too powerful and it's eliminating a lot of the differential rotation everywhere. So that's one thing that we need to investigate is as we change parameters, how can we get into a more solar-like regime where there's strong differential rotation in the convective zone. The other interesting thing that we found in this work is that radiative spreading can be achieved only at moderately low Prandtl number, which is good because it's slightly more computationally tractable to do Prandtl number 0.25, say, than Prandtl number 0.1. And the way we did this is we kind of sneakily noted that radiative spreading is so fast because it depends on the fourth power of that derivative. And so even if sigma is 3, which is bigger than 1, and you might expect radiative spreading to be weak, it's actually quite strong. And so you don't actually have to go to sigma much less than 1 to achieve the radiative spreading regime. So that was one sort of interesting novel finding of all this. So the really ugly thing, I think, is that, you know, we're doing our best. We're trying to get into the parameter regime we need to be. And what if we really do need solar-like parameters? Because we went down to Prandtl number 0.1, and that cost, you know, 10 million CPU hours. And what if we don't find the correct behavior until Prandtl number is 10 to the minus 6? So that's always um, the difficulty with these simulations is that you would like to be orders of magnitude away from where you are. And I think in summary, I think um, this is good that we can at least get large scale behavior that is what we want, even if we are orders of magnitude too far away. And then I'll just end with avenues for future directions. So one thing that I really like to do as part of COFFIES is work with Gustavo Guerrero and others to get an implicit large eddy simulation like OILAG to implement an explicit radiative diffusivity, but an implicit viscosity. So effectively, I think the ILES codes like OILAG could get into this radiative spreading regime more effectively than explicit codes like Rayleigh. And the way they could do this is have kappa rather high on purpose, but then have their implicit time stepping algorithm take care of the kinematic viscosity. And so effectively, you'd have very, very low new, but reasonably high kappa and effectively very low Prandtl number. So that could be a nice way to attack this problem of what if we need Prandtl 10 to the minus 6. The other thing that I want to think about with maybe flux emergence people is what is the non-axisymmetric quasi-periodic components of the solar cycle? Because I go all the way back, we're looking at in the simulations, we're looking at this m equals 1 mode at the Tachocline interface that's reversing quasi-regularly. And in the real system, we don't know the consequences of this for flux emergence, but can anything like this be observed um, in the data, say through active longitudes? So that's one thing I'm really interested in. What is the polarity of active longitudes, say the pairs on opposite sides of the sun? Okay, jumping all around. Um, and then the other thing that I wanted to work on, and this is possibly with Pascal and her colleagues on who are doing studies of fundamental of stratified turbulence, is for this to work in terms of the magnetic skin effect, we might need the diffusivity to be turbulently enhanced in the sense that there might need to be this stratified turbulence that's allowing the dynamo's magnetic field to actually diffuse significantly into the radiative interior. Um, and this could be caused by a number of things. There's shear instabilities, there's Rossby waves and gravity waves, Alfvén waves. And so I'm very curious to see where the studies in stratified turbulence go. Um, and then finally, as part of my NSF project, I'm looking at how all this occurs during spin down. And so what is the future of the tachocline in rapidly rotating stars versus slowly rotating stars, or as the convective Rossby number goes from very strongly rotationally constrained at 0 to weakly rotationally constrained at infinity. Okay, that's everything for me. Sorry for all the jumping around. I really appreciate your time and attention. I'm happy to answer any questions.
Thanks, Lauren. There are actually already some discussions in the chats. Let me
Okay.
recap quickly. Sushan asked a question about the multiple questions. I'm trying to find the original one. I'll let Sushan ask this because this is the most discussed one. Nick have help
Okay.
answered, and then Gustavo also follow up. And beside that, Todd also have a question about Poe. So let's do the
Okay.
first by Sushan's question because that's the most discussed one. Sushan, can you summarize your question? There are multiple ones.
Yeah, I was asking, and I think you answered it in the slides, about how different the viscosity magnitude is in simulations versus the
Oh,
real sun.
yeah, it's so if it depends on it sort of depends, but it's huge. It's like probably 10 orders of magnitude.
Oh, 10 orders. Okay. I thought it was
Yeah, in
maybe.
dimensional terms, like we want to be at, I think the viscosity is like 10 in CGS units, and then in a simulation, it's like 10 to the 11. So
Oh,
if you use CGS units, you can kind of fudge things around a little bit if you go non-dimensional, but probably 10 orders of magnitude is the radiative diffusivity is the only one that you can get more close to. Because that one's so high.
okay. The other question I had was, this whole study is an exploration of what can kind of spread perturbations or sharp gradients in differential rotation around, right?
Yes.
Uh, um, would it, what size of disturbances, what like length scale of disturbances would it apply to? I'm thinking of like in terms of like a flux emergence, like an emerging active region, the disturbances that it
Mm.
creates. Would these processes also apply to those disturbances and spreading those? And can we calculate a time scale for those?
Yes. Yeah, that's actually a really good question. So what happens is you can do that is all the way at the beginning. Um, and there's a paper um, by Alfred Clark in 1973 that basically does this is so I have twiddle equations here, but you can do the actual equations. So basically you linearize the Boussinesq equations. Um, and what you end up doing is you can break, because it's a linear problem, you can break apart all the disturbances into different eigenmodes. And so there's different horizontal wave numbers, and those spread at different rates. And so you can calculate. So the main disturbance sort of spreads on the Eddington suite time. But again, this is twiddle algebra. And if you did the actual algebra, you'd find that there was a bunch of other factors here that depend on the wave number of the disturbance. And generally, I think the smaller scale disturbances will spread more quickly. I forget exactly how it goes. But in terms of like actual numbers, I'm not too sure like if how this would relate to active region emergence for instance.
Okay, thank you.
Gustavo once asked about how small is differential rotation. Gustavo, is your question already clear, or you want to ask?
Hi, Loren, thank you.
Yeah.
So yeah, my question, you mentioned something about that, but from the figures, I don't understand the units that you use, but from the figures, even the hydro simulation seems to have a very small differential rotation.
That's true. So the differential rotation is like 5-6% probably.
And in the magnetic case is 1%.
Oh no, sorry, the hydro case is more. I'd call this 3. I'd actually call this 5% because the fast thing, I've plotted this in a way where like the difference between this is the MHD case, and the difference between equator and say 60 degrees, I believe, is like 4%. I'll say 4%. So no, it's quite weak. But in the hydro case, it's strong. It's more like, I don't know, 25%. So that's more in line with what we would expect. And the units, I'm dividing by the background frame rate, which is why the units might look a little strange. But no, I mean, it's a problem because anytime we can find the Tachocline, we also sort of mess up the differential rotation in the convective zone.
Yeah, and another question that I have is that you have this term that you say that is the radiative spreading, but is related to meridional circulation. Can you explain this better? And also, if you have a figure of the meridional circulation that can give a hint of what is happening with this term, should be really great.
Right. I don't know if I have a figure of them. I should have a figure of the meridional circulation. I think I can remember what the circulation does. So the reason this is the radiative spreading term is that we want to consider the torque, the angular momentum transport by the circulation, because in radiative spreading, it's this burrowing circulation that's transporting angular momentum. And effectively, the sigma parameter is supposed to be measuring the ratio of these two torques, because there's, one torque is the viscous torque, and then the circulation torque. And the problem is radiative spreading also involves a bunch of different stuff. It involves it's Boussinesq, it's in thermal wind balance, and it has advective diffusive balance of heat. And it has transport by circulation. And so what I've been basically doing is I have been investigating these other balances fairly carefully, and that will be in the follow-up paper. But if you take that on faith, then you can figure out then radiative spreading comes down to is the circulation what's spreading the angular momentum. I think that's the best way to look at things. So that's why I'm calling this tau MC, the circulation torque, the radiative spreading term.
But this does mean that you have some meridional circulation down in the radiative zone?
That's correct. And I don't think let me see if I have. I really should have that plotted, but I don't think I do. Um, and but what I can tell you sort of what it does. I'm not in full screen. I don't know if you can still, let's see. Play. Um, so basically what the circulation is doing is it's kind of impinging first in a very shallow region um, in the upper part of the radiative zone, and then it spreads with time. And I should include the circulation cells. Unfortunately, I don't have them right now. But for in the follow-up, what I can show you on I'll show you offline. You can look at radiative spreading as a function of time and kind of watch the circulation and the different rotations spread inward. But the key point is that the circulation impinges on the top part of the radiative zone and then kind of slowly makes its way inward.
Okay, thank you.
Okay. Todd also asked a question about the poles. Todd, are you there? Do you want
Yeah,
to?
I can ask it, or I mean, this figure actually shows it. I first noticed it in 18 and 20, but you've got some interesting things going on in the polar regions. Is that just numerical resolution, or should we be looking for something unusual in the polar regions that would show up in observations?
I mean, I'd have to think about that. So are you talking about these
Mm-hmm.
patches?
Yes.
Yeah.
Yeah.
So those things, I think they're real. However, I'm not sure why they arise. And I also need to make sure. So, I mean, the rotation rate is dividing by the moment arm. So I could imagine that these are weaker than you think. So that's what I'm not sure about. But I do think they're real in the sense that there are these vortices here because they're quite long-lived. But I need to check on what the actual amplitude is, and like would they actually show up? Like what do they look like if you and that is a good question. And I'm not sure, unfortunately. And
Yeah.
then and if there is something interesting, then no, that we should explore that for sure.
Yeah, well, I know Roger Ulrich has been looking at the historical data from Mount Wilson and has seen some, equatorward flows and then poleward flows at different parts of the cycle. And so Shant is also looking at features that are rotating at high latitudes, and it would be interesting to know what we should be looking for with
Right.
the.
All right. Well, no, I'll make note of that, and maybe if it's robust, I'll send some plots along.
Cool. I was going to say at the beginning, great work. So great work to you,
Thank you.
but and on all these things, I think it's really interesting that we're making progress on this. So thanks so much.
Oh no. Well, thanks for humoring my jumping around the slides.
I also noticed a comment from Sabarni in the very beginning of the talk. It's not a question, it's a comment. So I guess I'll just read out the comment, unless Sabarni, you want to just speak up about it.
Okay, I can do that. It's just that we know the position of the Tachocline very well till about 60 degrees. So the statement that we're not sure about the position is not completely correct. And the width is actually much smaller than 0.05.
Okay.
If we consider the very long time series data that are being produced now, and don't quote me on it, but it looks like as we increase the length of the time series and get more and more precise data, the thinner the Tachocline seems to be.
So it really is quite thin.
Yeah, very, very thin. So
okay, so I should update that.
Sarvani, you in your comment you write 0.025, and now you say.
I mean, it's much lower than that, but definitely 0.025 you might reach at the high latitudes.
Okay.
But around the equator, it's way smaller than that.
Okay.
So,
No, that's good to know. I think I need to update both my internal understanding and my slides. So
Hey,
if I can jump in,
sure.
just to follow up, both Sarbani and I and Antonio are in the process of finishing a paper precisely trying to measure very precisely where the tachocline is and how thin it really is. And hopefully those two papers will be submitted, within the month. And indeed, this use the longest time series that we have, including 25 years of gong data. And for those who don't get my emails, I'm also now reducing 30 years of gong data as one very long time series. So really trying
that sounds awesome. No, I
really trying to pull down, the precision of the measurements of the eigen frequency to try to get, the best possible characterization of the average tachocline. You have to realize that as we use a very long time series, if the tachocline moves around, it will look thicker than it really is if some of the characteristics change with the solar activity.
Now, can I ask, does this recent work, does this mean that the tachocline is exclusively in the stable layer?
No.
Okay.
At low latitudes, it's in the stable region. At mid latitude, it's in the convective region.
Okay.
High latitudes, it's a bit uncertain. It could be in the stable or maybe convection because the uncertainties get pretty large.
Okay. And I may argue that actually there are two tachoclines. There's a tachocline further in at low latitude where the shear is positive, and the tachocline location at high latitude is higher up where the shear is negative. And
yeah, you could put it that way if you wish. But
and I hope that in the plots I'm about to send to Sarvani, I'll convince her that I'm right.
Sounds good.
And but there is clear suggestion that clearly at mid latitude at 30 degrees there is no radial shear. So why do you define the tachocline there? And that's where I'm trying to convince people we have essentially two tachoclines, a low latitude deeper and a high latitude further out.
Okay.
Which was actually Antia and I had suggested that many, many, many years ago, but
I was about to add that
the data were just not good enough, and I'm not sure the data is still good enough. But we'll see. I'll wait for your plots.
Sorry, again, at the poles, it will be half in the radiative zone and half in the convection zone?
Well, okay, if you look at the central point of the tachocline, close to the poles, the position is quite uncertain, at least in the work I'm doing. I'm just talking about the center, but there's the finite width that we have to talk about. And I'm pretty confident of my results up to a latitude of about 60 degrees. Beyond that, it's so model dependent that things shift around too much and the uncertainties get pretty bad.
And at 60 degrees, it is?
60 degrees, it's sort of almost at the base of the convection zone, I would say.
Okay, so it will have
I can actually, if you allow me to share a figure, I'll share a figure. It's unpublished. The paper is being written as we speak, but it's there.
Do you want us to stop recording in that case?
Yes, if you could, please.
Resume the recording.
If
So
anybody has a bright idea what could cause, two different locations of a tachocline, do not hesitate to let us know.
Yeah, because if there could be a discontinuity in the tachocline, theoretically, that would be very interesting. Because till then, I'm keeping my mind open because the higher degree polynomial fits actually show a dip and then go. So you can simulate the dip easily.
The case of Belgian beer is what I offer if you have a good theoretical explanation.
Yeah.
Okay.
Yeah.
Sounds fair.
Looks like we can hear more about the Tachocline, another seminar from heliososmology environments, like in the fall or winter kind of time of another seminar. I will follow up with you guys, and thank you. So thank you today for both Loren and all the attendees, and thank you for staying here. Like I see already some people jumping off because of the other meetings. But anyway, see you next month, and thank you all.
Okay.
Thank you.
Bye.
Thank you.
Bye. Bye-bye.